Welcome, and thank you for joining us today. I'm Ryan Geister, Applications Engineering Leader, and joining me today will be John Murphy, Applications Engineer. It's our pleasure to introduce you to the latest Earthwise system from Trane, the CoolSense Integrated Outdoor Air System. Over the next 60 minutes, we'll share with you an emerging new system from Trane, which leverages sensible cooling terminal units and a dedicated outdoor air system. This offering has us excited to provide more system choices to our customers. We will explain how the system works, including control sequences, and then discuss the many nuances of the system. A few may be paradigm-shifting ideas for some viewers. We'll explore the requirements of the system, choices to be made, and how those choices affect system performance. We'll also take a look at chiller plants, my love, and how the unique needs of a CoolSense system will impact those designs. Specifically, the need for a dual temperature chilled water plant. And finally, we'll compare and contrast to existing systems and look at some energy comparisons. But first, let's look at some trends that spurred our interest in developing the Earthwise system. As buildings are designed for lower energy use, there is a correlating reduction in sensible cooling loads. Much of this is due to improved insulation, better glazing or shading, less air leakage, and tighter buildings, more efficient lighting, and even reductions in plug loads. As an example, in many applications, LED lighting is being used instead of incandescent or fluorescent light fixtures. With LED, the electricity use is less, and they also generate significantly less heat. This is one way that sensible cooling loads are being reduced. Consider this chart from the Design Professional's Guide to Net Zero Energy Buildings. As we look at the buildings with the higher space loads, depicted here, designers tend to favor systems like VAV or fan coils. But when buildings have lower sensible cooling loads, systems that use zone-level sensible only cooling equipment typically becomes more practical and more economically feasible. Sensible cooling is not a new concept. In fact, some common examples include chilled beams, radiant cooling panels, radiant floors, and terminal units with sensible cooling only cooling coils, like CoolSense. The common characteristics of all of these devices is that they provide sensible cooling only. The latent loads are handled separately by a dedicated outdoor air system. I've been asked, why introduce this system? Why now? As we continually evaluate new technologies and trends, we saw a need for a next-generation system that provides individualized comfort to each zone while minimizing the energy used for ventilation. As we just discussed, modern buildings are tighter, more efficient, and we seek integrated systems that are cost-effective and energy efficient, while maintaining comfort and indoor air quality. By separately conditioning ventilation air and then integrating its delivery with the heating and cooling system, building owners can minimize the largest energy component of the HVAC system, outdoor air used for ventilation. This is the primary driver in Trane's introduction of our latest Earthwise system. Now, we must acknowledge Trane did not invent this system. To our knowledge, it was developed when a design-build contractor was challenged to upgrade the HVAC systems to the Pentagon post 9/11. The project was complicated by very shallow ceiling plenums and a mixed climate with cold winters and humid summers, high loads, large outdoor air requirements, and the need to properly treat and protect the incoming outdoor air. Voila! The sensible cooling terminal unit system was born. So here we are. Trane introduces the CoolSense Earthwise system with the goal and purpose to go beyond traditional systems with an integrated packaged offering that minimizes the cost of conditioning outdoor air while ensuring occupant comfort. Now let's take a look at the CoolSense system. Here, each zone is served by a terminal unit equipped with a variable speed or ECM fan and a sensible only chilled water cooling coil. And here, a dedicated outdoor air system provides all the dehumidification needed to keep the spaces below a desired dew point. Then, the chilled water supplied to the zone-level terminals is controlled to a temperature that is warmer than the space dew point. Typically, the indoor dew point will be 55 degrees, and the chilled water temperature will be a couple degrees warmer, typically between 56 and 60 degrees, to ensure that the terminal units operate dry. Let's take a closer look at the sensible cooling terminal unit used in the CoolSense system. At first glance, this looks like a series fan-powered VAV box, but look here, a chill water cooling coil mounted on the inlet from the ceiling plenum. So how does this work? Conditioned air delivered from the dedicated outdoor air unit enters through the terminal unit through this air valve. The airflow measuring damper both measures and controls the outdoor air delivered to the zone. This is the same proven technology we've used in our conventional VAV terminals, but in this case, this valve is typically sized only for the minimum outdoor airflow required by code. Inside the box, the conditioned air mixes with recirculated air from the zone that passes through the sensible cooling coil to the variable speed fan, supplying the air into the downstream ductwork and diffusers. The CoolSense terminal units can also be equipped with hot water coil or electric heat. This offers flexibility in your system design based on climate and building use. This is a fairly simple device made with familiar parts that we've used for many years in more conventional systems.
As Ryan explained, that this cooling coil is intended to operate dry. That is, no condensation. We ensure this by properly designing the dedicated outdoor air system to keep the space dew point low. And then also by controlling the temperature of water delivered to this coil so it's above that space dew point. However, each Trane terminal unit also includes a drip pan located underneath this coil in the event that unintended condensation does occur. In this drip pan is a moisture sensor. If condensation was ever to occur, this sensor would trigger the condensate avoidance sequence that's pre-engineered into our factory-mounted controller. I'll cover this in more detail in just a bit.
And for those with the curious eye, there is a drip pan on both the bottom and the top of the coil. If you'd ever need to flip the box over during installation to better line up piping connections, the only thing you need to do is relocate the moisture sensor, a minor task. At this point, I'm going to turn it over to John to explain how the terminal unit is controlled.
This chart depicts the operation of the terminal fan, the chill water cooling valve, hot water valve or electric heater, and the ventilation air damper. Now the x-axis is sensible load in the zone, with heating to the left and cooling to the right. So for occupied mode, let's start with the zone temperature satisfied. That is, the temperature is in the dead band between its heating and cooling set points. In this dead band, the fan operates at its minimum airflow set point, with both the chill water and hot water valves closed. Now I'm showing 20% minimum airflow as an example, but this is an adjustable setting. Meanwhile, the ventilation damper is controlled to the current minimum outdoor airflow set point. If demand-controlled ventilation is used, this will vary between the design outdoor airflow for the zone and some minimum airflow threshold. That's why I depict this as a range rather than as a single line. I'll talk more about demand-controlled ventilation in a few minutes. Now, when the temperature in the zone rises to the cooling set point, let's say 75 degrees, the controller attempts to maintain zone temperature at this set point by modulating either the terminal fan speed or chill water valve. The hot water valve or electric heater remains off. Moving from this dead band to the right, the controller first modulates this chill water valve further open, while the fan remains at its minimum airflow set point. This is the first stage of cooling. When the requested cooling capacity has increased to the point where the chill water valve has opened to 100%, the controller then begins to increase the fan speed, while this chill water valve does remain at 100% wide open. This is the second stage of cooling. Now so far, the ventilation damper is still being controlled to the minimum outdoor airflow set point. So it's bringing in only as much outdoor air as needed for ventilation. But the Trane controller has an added feature which we're calling a cooling boost mode. With the chill water valve fully open, if this fan reaches its maximum airflow set point and the zone still requires more cooling, the controller can modulate the ventilation air damper further open. This will increase the flow of cool, dehumidified air from the dedicated outdoor air unit. Now, note that this boost mode is not intended to be typical operation. The terminal unit should be selected to offset the design space-sensible cooling load with the fan at full speed and the chill water valve 100% open. This boost mode is meant for unintended situations that might not have been considered when sizing, like 30 people cramming into a conference room that was designed for 20. This maximum damper airflow set point is an adjustable setting, so you can decide how much or how little boost you want to design in. Now let's move to the heating operation. When the temperature in the zone drops to its heating set point, let's say 70 degrees, the controller attempts to maintain zone temperature at this set point by modulating the terminal fan speed and the hot water coil or electric heater. In this case, the chill water valve now remains closed. Moving from this dead band to the left, the controller first begins to increase the fan speed. This recirculates warm air from the ceiling plenum to maintain zone temperature. In this first stage of heating, the hot water valve or electric heater remains off. When the requested heating capacity is increased to the point where the fan has reached its maximum airflow set point, the controller then begins to modulate the hot water valve further open, while the fan remains at maximum airflow. This is the second stage of heating. Now in heating mode, the ventilation damper is controlled to the current minimum outdoor airflow set point. There is no boost mode for heating since the temperature of the ventilation air is typically not warmer than the zone during occupied mode.
We hope this explanation offered the necessary details to demonstrate how these CoolSense terminal units operate. It should be noted that these control strategies are integrated directly into the factory unit-mounted controller. If you want to learn more, it can also be found in the CoolSense Systems catalog or the Terminal Unit catalog. So John, a couple questions often do emerge at this point. First, the boost mode you referred to. Is it fair to say that this functionality offers designers additional flexibility? I mean, if there was a planned future tenant fit-out, could an engineer select an air valve larger to enable more DOAS air to be available to the box for some future risk avoidance?
Well, it certainly provides flexibility in the selection process. Say you have an office floor plan and you want to design in a little reserve capacity for future changes. For that, you might choose to upsize a dedicated outdoor air unit and ductwork. But what if you're selecting a unit for a 20-person conference room? You might rely on this boost mode to provide a little more capacity in the event that 30 people ever cram into that room. But in this case, you might not change the size of the dedicated outdoor unit and ductwork if the people in the conference room are expected to come in from the adjoining office spaces. In either case, though, if demand control ventilation is used, I'd be careful to not oversize the air valve too much since you want to control accurately at all airflows, including low airflows too.
A second question. For an engineer laying out a job, is the standard sequence of operation that any sensible cooling box could offer? Or is this proprietary to Trane?
Well, there are multiple manufacturers of sensible cooling terminal units, but Trane is the only one we know of that has pre-engineered these sequences into a factory-mounted controller. Others use custom programming and field-installed controllers. Note that there's nothing proprietary here. In fact, I just told you how it all works. Just be sure to clearly specify the sequences.
Now please show us what else is programmed into the controller to support the CoolSense system.
Well, since 100% outdoor air is delivered to an airflow measuring damper in each terminal unit, implementing demand control ventilation is very straightforward. When a zone CO2 sensor is connected to the controller, the demand control ventilation sequence will dynamically adjust outdoor airflow by modulating the ventilation damper based on the current CO2 concentration measured in the zone. Now, this chart depicts how the ventilation damper responds. When the zone CO2 concentration is at the high limit, the ventilation damper is controlled to bring in the design zone outdoor airflow. This is what their code requires at design zone population. When the concentration is at the low limit, this damper is controlled to bring in the DCV minimum outdoor airflow. This is the amount of outdoor air required when no occupants are currently present. It's typically the CFM per square foot rate that's listed in ASHRAE standard 62.1. And then when the concentration is between the low and high limits, the damper modulates proportionally between these two airflow set points. Note that this is the same sequence that's described in the standard 62.1 user's manual. Now, if an occupancy sensor is used instead of CO2, the damper brings in either the design outdoor airflow when the zone's occupied, or this DCV minimum airflow when no people are present. So this purple line defines the minimum airflow set point for the ventilation damper. Most of the time, it's bringing in only this minimum airflow required for ventilation. But remember, in a sensible cooling system like CoolSense, this dry air from the dedicated outdoor air system is the only source of dehumidification. So when you decrease outdoor airflow with demand control, you're also providing less dehumidification. Now, if the only latent load is due to people, that's probably not an issue. If the people are not there to generate CO2, they're also not generating humidity. Even so, the Trane controller contains logic that will override this demand control ventilation if additional dehumidification is required. So if you install a humidity sensor in the zone, it's used to calculate the current zone dew point. If that dew point rises above the entering water temperature, the controller will temporarily close the chill water valve and modulate this ventilation air damper further open. This overrides demand control and increases the flow rate of the dry air from the dedicated outdoor system to lower the zone dew point. Then the chill water valve will be allowed to open again. Now this ventilation damper has a separate maximum airflow set point, which can be set even higher than the design outdoor airflow if desired. Just like the cooling boost mode, this gives you the flexibility to provide a boost of dehumidification to a zone where the latent load might be higher than you estimate. In addition, like I mentioned earlier, all Trane terminals are built with a drip pan located underneath this sensible cooling coil. If the moisture sensor in this drip pan ever detects the presence of condensate, the controller temporarily closes the chill water valve and continues operating the fan and ventilation air damper as normal. Once condensate is no longer detected, the valve is allowed to open again.
At the core of the system is that CoolSense integrates ventilation control into the zone-level cooling and heating terminals, thus providing individualized comfort to each zone while minimizing the energy used for ventilation, a key outcome for designers looking toward net zero energy buildings. Before we move on, one more concept related to condensation is a mode we call morning dryout. While we did not invent the term, it's a new one for many. And to help explain, I start with a familiar phrase, morning warm-up. When the building is unoccupied, we typically let the temperature drift to save money. In the winter, we let it get colder. In the summer, we let it get warmer. Then we proactively set a time when the system needs to start such that the building is back to set point when it's time to occupy the space. No big deal, and it's easily understood. However, for sensible cooling systems like CoolSense, we have spoken about the need to control the dew point in the space also. Consider a school during warm, humid weather. When unoccupied, we allow the temperature to drift warmer inside the building to save the energy. But we know that at the start of the school day, say 7 a.m., hundreds of children are going to be flooding through the wide open doors and into that school, bringing significant latent loads into the building. So for CoolSense, the morning dryout means starting the system earlier, before the kids arrive, to proactively pull down the RH, the dew point, to minimize the risk of condensation. Next, we'll take a deeper dive into a key component of the system, the dedicated outdoor air unit. As I've been traveling and talking about this system with customers, it seems everyone has their own, often strong, opinion on how a DOAS unit should be configured. While we can offer many configurations, we've pulled together 6 configurations we think make a lot of sense for CoolSense, and many customers can relate to these 6. Of course, there's always the simplest option, a standalone DX dedicated outdoor air unit. Others will choose to use a chilled water air handler, which can offer greater flexibility and more opportunities for improved efficiency. Before we look at these configurations, however, John, I think it's important to discuss the needed dew points required by the dedicated outdoor air unit in the CoolSense system.
Again, in a sensible cooling system like CoolSense, the dry air from the dedicated outdoor air system is the only source of dehumidification. So this air must be dehumidified to a dew point that's dry enough to offset the entire space latent load and maintain the indoor dew point below about 55 degrees. As an example, let's consider a typical office space. Assuming the only latent load in the space is due to people, the ASHRAE handbook suggests a latent load of 200 BTUs per hour for each person doing active office work. Then, ASHRAE standard 62.1 requires 5 CFM per person plus 0.06 CFM per square foot for an office space. Using the default occupant density, this equates to 17 CFM per person. Finally, a 55-degree dew point in the space equates to a humidity ratio of 65 grains per pound. Solving the latent heat equation here, this dedicated outdoor unit must dehumidify this quantity of air to 48 grains per pound in order to offset this space latent load. This equates to about 47-degree dew point. Of course, you could choose to increase this airflow, allowing for a higher leaving air dew point, but this would require the size of the dedicated outdoor unit and the ductwork to be larger.
Using that example then of 47-degree dew point for an office space, now we'll look at a few dedicated outdoor air unit configurations that can be used to dehumidify the outdoor air to this required dew point. The first configuration uses a total energy wheel to precondition the entering outdoor air by exchanging both the sensible and latent heat between the outdoor and the exhaust air streams. The air then passes through a cooling coil and possibly a reheat coil before the fan discharges it into the ductwork. Shown here is the cooling coil. As mentioned earlier, this also could be a DX unit. Now look here, the recirculating the air damper. This is a key piece that can be seen in all configurations. These dampers can be used for a variety of control strategies, including the morning dry out mode I mentioned earlier. By closing the outdoor air dampers and opening these recirculating dampers, this changes the DOAS unit into a giant dehumidifier that dries out recirculated air if necessary to lower the dew point.
Here's this unit depicted on a psych chart. This is an example of a warm, humid day. The total energy wheel transfers sensible heat and water vapor to this cooler, drier exhaust air stream. This reduces both the cooling and dehumidification loads. The cooling coil then dehumidifies this air to the required 47-degree dew point. Now in this example, we're conditioning 20,000 CFM of outdoor air. So the load in the coil is 107 tons. Note that if we didn't use energy recovery, this load would have been 172 tons. Now for this example, with the exception of a few degrees of heat gain from the fan, I'm showing this dehumidified air not being reheated. So it's delivered down the duct at 49 degrees dry bulb. Now because this dehumidified outdoor air is colder than the zone temperature set point, it will offset part of the zone sensible cooling load. This allows the sensible coils in the terminal units to be smaller. At 49 degrees, 20,000 CFM of this cold air will offset a total of 47 tons of the sensible cooling load in the zone.
I'd like to reinforce a couple of key points just made. First, the unit delivers 49-degree air down the duct at a 47-degree dew point. For this example, we're assuming 40-degree water or glycol is needed to achieve this. Second, the required cooling capacity is 107 tons. If the total energy wheel was not used, it would have been 172 tons, a substantial reduction of 38%. Finally, the cold air delivered to the terminal units is offset by 47 tons of the space-sensible cooling loads. Next, we'll look at a simple enhancement to this configuration. Now, focus your attention right here. This is the same air handler, but now it has two cooling coils in series instead of just one. The same 49-degree leaving air, same 107 tons, but now this capacity is divided between two coils. The downstream coil receives the same 40-degree water needed to achieve the 47-degree dew point, but the upstream coil can receive warmer water. The chiller plant is sending 57-degree water to the sensible cooling coils in the CoolSense terminals. By adding this upstream cooling coil, we can shift 30 tons of load to the warm water chiller. That is, some of the load is shifted to the chiller operating with less lift, reducing the load on the tougher duty chiller that's making 40-degree water for dehumidification and ultimately lowering the chiller plant energy. This is not required, however, but it can be valuable if you're trying to maximize overall efficiency or minimize the size of the cold water chiller. Now let's move on to the second unit configuration. I've gone back to this single cooling coil, but now I've added a desiccant dehumidification wheel in series with the cooling coil. That is, one side of the wheel is upstream of the coil and the other side downstream. This is Trane's branded CDQ technology. This configuration offers some significant advantages. First, since the desiccant wheel provides further dehumidification downstream of the coil, the cooling coil requires only 45-degree water to achieve the required 47-degree leaving air dew point. And in this case, the required cooling capacity drops to 96 tons compared to the 107 in the first configuration. Finally, notice that the leaving air dry bulb is now 55 degrees. For those engineers who are not comfortable sending 49 degrees down the ductwork, this might alleviate their concerns. There are some drawbacks, however. The desiccant wheel increases the physical size of the unit and adds pressure loss to the airstream, which does impact fan energy use. And by delivering warmer air to the CoolSense terminal units, it offsets less of the zone sensible cooling load, requiring the sensible coils to offset more of the space load. This might require larger coils in the terminal unit, a higher water flow rate, or both.
After air leaves the cooling coil, it passes through the downstream side of the CDQ wheel. This desiccant absorbs water vapor, further dehumidifying the air. In this example, the cooling coil need only dehumidify to a 52-degree dew point because the desiccant wheel dehumidifies it the rest of the way to 47. So the coil load is reduced to 96 tons compared to 107 tons without CDQ. And because the cooling coil only needs to make 52-degree air, the chill water supplied to it may not need to be as cold. In our example, we're using only 45-degree water compared to 40 degrees in the configurations without CDQ. Now, this process of absorption does release a little bit of sensible heat, and so the air leaves the unit at 55-degree dry bulb and 47-degree dew point. Now, as Ryan mentioned, this warmer air offsets less of the zone sensible cooling load, requiring the terminal units to provide more of the sensible cooling capacity. So what happened here is the CDQ wheel shifted 11 tons of load from the dedicated outdoor unit to the sensible coils in the terminal units. That's load shifted from the cold water chiller to the more efficient warm water chiller.
Now once again, same DOAS unit, just adding the upstream warm water coil and splitting the load again. Here you see that this shifts 37 tons of load to the warm water chiller, further reducing the load on the cold water chiller from 96 tons to 59 tons. Now only one more configuration. No CDQ wheel here, but now we have included a fixed plate sensible heat exchanger located downstream of the cooling coil. This device transfers sensible heat from the warm exhaust air to reheat the cold dehumidified air. This configuration provides unique benefit that the heat exchanger pre-cools the exhaust air, allowing the total energy wheel to pre-cool the incoming outdoor air even further. Note we're still delivering the same required 47-degree dew point, but this time at 64-degree dry bulb. This shifts even more load from the dedicated outdoor air unit to the terminal units. So this results in the smallest capacity cooling coil, only 85 tons.
The different component in this configuration is the downstream fixed plate heat exchanger. This device transfers sensible heat from the warmer exhaust airstream to reheat the cool dehumidified air to 64 degrees in our example. On the other side, this exhaust air is cooled down to about 57 degrees. Now with this cooler exhaust air, the total energy wheel provides an even greater benefit, pre-cooling the incoming outdoor air to 66 degrees, quite a bit cooler than without the downstream heat exchanger. Now this added pre-cooling benefit reduces the load on the cooling coil to 85 tons compared to 107 tons without it. But again, the fixed plate heat exchanger impacts the physical size of the unit and adds pressure loss. And the warmer air leaving it offsets even less of the zone sensible cooling load.
And again, same as before, this configuration can also benefit from using separate chilled water coils in series. Here, 8 tons of cooling load is shifted to the warm water chiller, reducing the load from the cold water chiller from 85 tons to 77 tons. So let's look at some takeaways. This table transfers all those values from the 6 different DOAS configurations and adds in the standard DX unit for comparison. Focusing in on the red values, this comparison shows a designer that can leverage different DOAS configurations to advantage their design, shifting loads to the warm water loop or the cold water loop, depending on the application and desired chilled water plant configurations. More on that in a moment. First, in the far left column, the DX dedicated outdoor air unit with the hot gas reheat, certainly the least expensive of all options, shown here without any exhaust air heat recovery. Moving to the next column, the chilled water DOAS unit with total energy wheel. It's the simplest of the water-cooled configuration designs with the smallest footprint. It also delivers the coldest air at 49 degrees compared to 55 degrees or 64 degrees with the other 2 configurations. This allows the zone level terminals to be downsized the most, but some designers are concerned about downstream duct insulation or condensation issues with this cold of air. As we move across the table, the loads shift between the warmer loops and the colder loops, shifting more load to the terminal boxes. The key takeaway? The CoolSense system has multiple degrees of freedom for the designer, enabling flexibility and customization of their designs using the basic building blocks that the industry is already comfortable with. So the load that we are shifting around means the chiller plants have substantial opportunities for customizing too. John, let's start with the fundamental difference from a traditional chiller plant.
As we discussed, the chilled water supplied to the sensible cooling terminals is typically between 56 and 60 degrees to avoid condensation. But in order for the dedicated outdoor air unit to dehumidify enough to keep the indoor dew point below 55, the chilled water supplied to it will likely need to be in the range of 38 to 45 degrees. Now there's a wide variety of plant configurations that can deliver these 2 different temperatures, whether a single chiller is used or multiple chillers. So I'll start with maybe what's most the basic configuration, a single chiller dual temperature plant. Here, the chiller produces 40-degree fluid, either a water or water glycol mixture. Some of this fluid is distributed to the cooling coil in the dedicated outdoor air unit for dehumidification. while the rest passes through a plate and frame heat exchanger with a valve that's controlled to produce 57-degree water on the other side. This warmer water is then distributed to the sensible cooling coils in the terminal units. The benefit of this configuration is its simplicity. The control valve for the heat exchanger is selected and controlled just like the valve on the dedicated outdoor air unit. And the delta T selected for the chiller and outdoor air unit is independent of the delta T selected for the terminal units. Plus, if glycol is needed for freeze protection, the heat exchanger isolates the glycol to only the water chiller and dedicated outdoor air unit. Pure water is used on the indoor side of the heat exchanger, so the terminal units are not affected by the glycol. Now there are certainly other plant configurations possible, single or multiple chillers, air-cooled or water-cooled, and each has its own advantages and drawbacks. Even though there's lots to talk about, we just don't have the time in this length of video.
John, as you point out, it's notable how simple the CoolSense chiller system can be, but ice is just too good a match for CoolSense to not at least show the viewers one more chiller configuration, one that uses ice to make 40-degree fluid and the chiller to make the warmer water temperature.
Okay, I said this single chiller configuration is simple, but the chiller needs to make 40-degree fluid whenever outdoor conditions require dehumidification. So you don't get any efficiency benefit of operating a chiller at the warmer temperature used for sensible cooling. One way to gain that efficiency benefit is to use more than one chiller. We show those configurations in the system catalog. But another way is to add ice storage to this single chiller plant. First, we pipe in the tanks and a blending valve downstream of the chiller. And we add a building bypass pipe for charging the tanks at night. So far, this is just like a regular air-cooled chiller with ice, which we've been doing for decades. The new part is to move the cooling coil in the dedicated outdoor air unit, along with this blending valve, from this loop over to a new loop with its own set of pumps. This allows the ice tanks alone to serve the dehumidification load. So during daytime operation, the ice in the tanks is melted to produce the 40-degree fluid needed for dehumidification. This allows the water chiller then to raise its set point and make warmer fluid for the sensible cooling terminals. So the chiller operates more efficiently. Then, when the building is unoccupied at night, the chiller switches to an ice-making mode, lowering its set point to refreeze the water inside the tanks for the next day. Now this configuration provides the added benefit of shifting the cold water load, that's the dehumidification load from the outdoor air unit, shifting it to the nighttime hours when the cost of electricity, including demand charges, is likely to be lower. Now if you add a diverting valve and a connecting pipe, and also add a second cooling coil to the dedicated outdoor air unit like Ryan showed earlier, you can further enhance the flexibility of this configuration to operate only the chiller during daytime hours, in the event that ice is not available, for example. This also allows the plant to provide cooling or dehumidification for the building at night, while the chiller is also making ice.
John, time well spent. In the catalog, you will find many configurations of the dual temperature chiller plants, as well as the DOAS configurations we discussed. As we wrap up, let's compare CoolSense to another sensible cooling system, chill beams, since they are relatively well known and the most similar system type that separates sensible and latent cooling. First, a CoolSense system will typically have smaller ductwork and a smaller air handling unit. Why? Because with CoolSense, the dedicated outdoor air unit and ductwork is typically sized for only the minimum required ventilation air. In contrast, for many applications, the active chill beam system requires the primary air handling unit and the ductwork to be sized to deliver enough primary airflow to also induce sufficient room air for sensible cooling. We've done previous work in this area and have listed the Trane Engineers newsletter on active chill beam systems in the bibliography. Also, there are typically fewer terminal units, as a CoolSense system uses one terminal unit per zone in most cases. The terminal fan allows for higher cooling capacities per area of coil surface than using an induction in chill beams. In contrast, typically multiple chilled beams are required per zone. Next, CoolSense is more easily reconfigured if the use of the space or occupancy changes. Reconfiguring a zone often requires moving only the downstream flex duct and supply air diffusers. The terminal units and water piping often do not need to be moved, whereby active chill beams are also your diffusers, so the beams themselves often need to be moved, which also means reconfiguring and reconnecting water piping and primary air ductwork. Since neither the CoolSense system nor chill beams have drain pans, no need for movement of any condensate lines. That said, CoolSense does have a drip pan to catch any unintended condensate, whereas most models of chill beams do not. So any unintended condensate might drip into the occupied space. The CoolSense terminal units have the option to be equipped with a filter upstream of the sensible cooling coil to keep the coil cleaner and clean the locally recirculated air for improved IAQ. This is not an option for most active chill beams. The need for filtration of recirculated air could be discussed, rather debated, at length, but this will remain a topic for another time. Next, as we discussed earlier, it is easy to implement demand control ventilation, or DCV. After all, the CoolSense system integrates the outdoor air, meaning that 100% of the outdoor air is flow measured and integral to each zone level terminal unit, which makes demand control ventilation straightforward to implement. And as John mentioned, we've pre-engineered this into our controller along with overrides or boost to help if zone humidity gets too high. In contrast, in a chill beam installation, separate zone level dampers in the primary air ductwork are required to implement DCV, which adds costs and complexities. Lastly, because CoolSense has a fan, the DOAS or central fan does not need to operate to heat or cool the space. This is an advantage during the unoccupied mode, as only the terminal fan in the zone that requires conditioning needs to operate. The DOAS can remain off, assuming, of course, no dehumidification is needed. In contrast, a chilled beam system always requires the primary air handler to be operating if cooling or heating is needed at any time, occupied or unoccupied, since active chill beams require primary airflow for induction to occur. Further, unless the primary air ductwork is equipped with zone level dampers, the primary air handling unit will supply air to all the zones, even if only a few zones require conditioning. This can be a major source of the energy savings of CoolSense over chill beams. All of this leads to significant savings in first cost, as well as operating costs. So what are the potential considerations when using CoolSense rather than an active chill beam system? Well, there is a possibility for more maintenance to be performed in or near occupied spaces. If, for example, you want to use a filter to clean the recirculated air and improve IAQ, the filter would need periodic inspection and or replacement. Other than this, there's no other planned maintenance required after commissioning. Since each terminal unit is equipped with a fan located near the occupied space, there is also potential for higher sound levels. Obtaining a manufacturer's sound data that is tested and measured in accordance with AHRI's Standard 880 can help predict sound levels in the space. If a sound issue is identified, actions can be taken. The CoolSense catalog contains example acoustic analysis for an office space and or classroom. For the example, we modeled the K-12 classroom down to 35 dBA. A practical element that has come up in discussions with customers is the placement of the CoolSense terminal unit. If sound and maintenance is a concern, you might simply locate it over the corridor and duct airflow into the space. For the school example, this would allow maintenance staff to change the filters without disrupting class, and the noise would more easily be attenuated. So let's review the benefits of Trane's new CoolSense system. It offers efficiency advantages through the variable speed ECM fans, dual temperature chilled water plant, and minimizing of ventilation air, all while maintaining space comfort through individual zone control of both temperature and humidity. Maintenance issues are minimized with no condensate system. And at the building owner's discretion, filters can be added to the terminal units to improve IAQ. The design offers flexibility with box orientation, options for electric or hot water heat, all while minimizing duct size and cost. And for the designer, they can build in flexibility for the future via boost mode with a system that's easy to reconfigure if the space changes. Interestingly, as we have been working with many customers throughout North America, we've found benefits that go beyond the energy and design flexibility already discussed. For example, engineers and contractors are able to easily leverage their existing knowledge of project planning and estimating, as the pieces of the components and the components themselves are similar enough to traditional systems. Granted, there are nuances, but in general, the pieces are known entities and offer traditional trades comfort when bidding and installing the system. The low-height terminals, roughly 10.5 inches tall, along with smaller ductwork and no condensate drain system, requires less plenum space and potentially higher ceilings. And because there is a drip pan on either side of the cooling coil, the terminal can easily be flipped upside down to resolve installation constraints. Factory-mounted controls and standard programming for the terminals mean that the controls technicians can get on and off the job quickly and deliver a system that just works. Notably, wireless controls shorten the time to install dramatically. More benefits continue to emerge, especially as it's compared to other traditional systems. We also discussed the many nuances in controls that have been thought out and pre-programmed into the Trane controller. We know the control sequences are vital to system operation, including the terminal units, chiller plant, the dedicated outdoor air unit, and the global integration of all the subsystems. In an effort to help engineers properly lay out the jobs and obtain competitive bidding, Trane offers these sequence of operations, points lists, and control drawings in our prepackaged solutions system. This helps ensure engineers can specify the system, obtain competitive bidding, and minimize risk of missing details for their projects. This documentation is available at traneengineer.com.
To better understand the energy performance of this system, we used the whole building energy analysis software Trace 700 and modeled a mid-size office building. For our example, we compared the CoolSense system to an active chill beam system and a high-performance VAV system, and also to the ASHRAE 90.1 baseline VAV system. The chill beam system used 4-pipe active chill beams and separate constant volume primary air handlers for perimeter zones versus interior zones, each having a total energy wheel. The CoolSense system terminal units had variable speed fans, hot water heating coils, and demand control ventilation. The dedicated outdoor air handler also had a total energy wheel. Now, both the chill beam and CoolSense systems used separate chiller plants, one supplying 57-degree water to the terminal units and the other supplying colder water to the air handlers. Now finally, the high-performance VAV air handler had a total energy wheel and employed demand control ventilation, fan pressure optimization, and supplier temperature reset. And this system was served by a single temperature chiller plant. Now in this chart, the y-axis is the annual HVAC energy as a percentage of the 90.1 baseline, which is the left-hand column for each of the 4 cities modeled. Now column 2 for each city is the active chill beam system. Column 3 is CoolSense, and column 4 is high-performance VAV. Note that each of the 3 systems use considerably less energy than the baseline. Now for this example building, the CoolSense system, column 3, used less HVAC energy than the active chill beam system, which is column 2. About 15% less in Atlanta, 21% less in Los Angeles, 6% less in Minneapolis, and 13% less in Washington, D.C. There's more discussion of these results in the system catalog.
To conclude, we hope the discussion of the CoolSense integrated outdoor air system offered insights into a new system choice, possibly for your next project. The concept is simple. The pieces and components are familiar. Occupants enjoy comfortable spaces, while building owners enjoy lower energy bills. The CoolSense system's configurability, both in layout and supporting systems, like DOAS and the chiller plants, offers the engineer and architect significant flexibility in layout and design. If you have questions or want to discuss further, contact your local Trane office or look here. Thank you for joining us today, and now it's time to go beyond.